for us to have a non-evolving population, we have to meet 5 conditions. Okay, so 5 conditions must be met. Number 1, we're talking about a population here, so imagine a population of organisms. Number 1 is there has to be random mating. There must be random mating. What this means to you guys is that you cannot be choosy in your mate. There's no choosiness. So if you think of organisms, some organisms choose their mates based on the plumage, the coloration of the feet. Humans choose mates on intelligence, attractiveness, what have you, humor, etc. So we're not choosy in our mates. It's totally random, so random mating. If we are choosiness in our mates, we're going to change our allele frequencies, and we do not want to do that. Okay? Number 2 is there's no mutation in our population. I told you guys that mutation is a big driver of evolution a long time ago. So if you have a mutation, what can happen is you can introduce new alleles with a mutation. If I introduce a new allele, I change the frequency of my alleles, and I don't want to do that. Okay, so no mutation, because mutation can change the frequency of P's and Q's. Number 3 is there's no selection. No selection. What that means is that we are all equally likely to reproduce. Everybody in our population has an equal chance of reproduction. So there's no differential reproduction based on the alleles you inherit. So if I'm big A, and Issa's little a, we're going to reproduce at the same rate. So it doesn't matter what alleles you inherit. So there's no selection. Number 4, there's no migration. No migration or immigration. Okay? So in our population, we do not want individuals coming into it because they bring in new alleles. If they bring in new alleles, we change our allele frequency, and we do not want to do that. If people leave our population, we lose alleles, right? We lose some allele combinations. All right, so there's no migration, no immigration in our population. And the last one is a little bit more difficult for students to get. The last one is you have to have an infinitely large population. So we have a huge population. Why is that? It's because we want to minimize something called genetic drift. So we're going to minimize genetic drift with our really large population. What is genetic drift? I haven't gone over this term. I'm going to define it right now. Genetic drift is fluctuation in allele frequency due to chance. Okay, so genetic drift is fluctuation in allele frequencies due to random chance, randomness. And genetic drift really affects small populations. And I'll give you guys a concrete example. It's kind of gruesome, so hold on. So let's say we are a population here. This is a small population. We are subjects to genetic drift. Let's just say something random happens. Half of the ceiling in here caves in and squashes half of us. That means that we only have, let's just say we only have 7 individuals that survived. And just randomly, those 7 individuals are all homozygous recessive. We've just lost the big A allele because we had a small population. All right, and that would change our allele frequencies. If we only had individuals with the homozygous recessive individuals left, that means our Q up there is going to go to 1, and we've just lost P. Okay, so genetic drift is fluctuations in the allele frequencies due to random chance, and it affects small populations. If I cram a couple thousand, or let's go bigger, if I cram 1 million people in here and the ceiling caves in and it kills off 1,000 of us, that's okay. It doesn't change our allele frequencies nearly as much. Okay? So we need a large population to minimize genetic drift. All right, so the power of Hardy-Weinberg is that you can look at populations in the wild and assess whether the trait you're looking at is being selected for or against. In other words, is the trait you're looking for evolving? Now, if the population that you're looking at conforms to the Hardy-Weinberg equilibrium here, or equation here, it says that population is not evolving, or that trait in that population is not evolving. However, if your population does not match the Hardy-Weinberg equilibrium, it says something interesting is happening, that your population is evolving, probably. Okay? All right? Is everyone clear on the Hardy-Weinberg equilibrium? Not too bad. Now, the cool thing about this equation is it allows you to assess how many heterozygotes you have in the population. Okay, that's one useful thing for this equation, is you can assess how many heterozygotes you have. Heterozygotes, it's hard to assess them because they express the dominant phenotype. They look like homozygous dominant individuals. Okay, and so I want to do a short exercise to demonstrate this. And I'm going to pick on tongue rolling one more time. This is it, I promise. Okay, so how many, so 2, 4, 6, 8, 10, 16, 18, 19, 20, good. So we have 20 people. So in our population, we have 20 individuals. And how many are tongue rollers in here? 2, 4. Put your hands up if you are. Hi. Tongue rollers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 tongue rollers. And that means we have 9. That's a lot. So we have 9 non-tongue rollers. Okay, and if I say tongue rolling is due to a single gene, it is encoded for a single gene, and it's dominant. All right, so I'm saying tongue rolling is T dash. It's a dominant trait. And our non-tongue rollers are homozygous recessive. Okay. Now, what I want you guys to do is figure out how many heterozygotes we have in the population. All right, so the question is, how many pets are in the population? And remember, our population is very small, so take it with a grain of salt. But how many pets are in the population? And you know you're going to use these equations. P plus Q equals 1. P squared plus 2pq plus q squared equals 1. Okay? This is allele frequencies, remember? These are allele frequencies. And this is genotype frequencies. And we know, so P plus Q equals 1 is allele frequencies. P squared plus 2pq plus q squared equals 1 is genotype frequencies. And we know one of our genotype frequencies. Do we not? Does anyone want to help me out here? So which genotype frequency do we know?
Q squared.
We know q squared, right? So q squared is little t. This is. Okay, so we know q squared. So what are we going to do mathematically here?
9 divided by 20.
By which number?
20.
9 by 20?
Yeah.
Yep, so q squared equals 9 divided by 20, which equals, please, someone help me out.
0.45.
0.45. All right, so does this mean we can get a Q? Yeah, so Q is going to then be the square root of 0.45.
To 0.67.
Which equals 0.67. Great, so that's our Q. I'm going to put it up here. Q equals 0.67. That means P, we know P, right? Because P plus Q equals 1. And we know Q. We can easily get to P. Okay, now that we have our P's and Q's, we can get the heterozygous. How many heterozygotes are in our population, right? So someone please do the calculation. So our our genotype frequency of our heterozygotes is 2 PQ, which is 2 times 0.67 times 0.33, and that is what exactly? Sorry, you say it loud.
0.44.
0.44. So of the